Hello, IB Physics. In class on October 1st, we actually looked at your data from the Pendulum lab. And the way that we looked at it is that I have pulled a number of pieces of data that were submitted just to point out some things that we're going to be thinking about as we continue to do labs. Different ways of representing data, thinking through uncertainties, and then really understanding what are the results of our Pendulum lab. So first off, take a moment to look at these two representations of data. So they're both data tables. They have a lot of similarities, but take a moment, think about what could make it easier to interpret the data. So you might notice that we have our averages. We can sort of read those. We can see that here the averages are staying pretty similar. Here they're going up and then down. But if we look at the numbers themselves, there's a pretty big spread in the data that is collected. And so when we're representing data, we're ultimately going to be making graphs to make it a little bit easier to represent. Another thing I want to point out about these two representations is that both of them have written down their units while they're writing down their data. And that is a good thing. But it kind of takes more time. And so the reason we have headings on our data table is to make your life easier. In science and math, often we do things to do less work. We want to be as lazy as possible. And so the way we do this in science with our data is that in the data table, we'll write the units up here. We have it in this data table, but that's really helpful. Another thing you'll want to make sure that your data table has along with your units is our uncertainty. And here we have a plus or minus blank, which is understandable. We're still a little struggling with this idea of uncertainty. Maybe you can think about what the uncertainty should be for the measurement of the period. But that's something that's really helpful to think about, making sure that your heading is as informative as possible. Looking at these data representations, again, we can maybe see some patterns just by looking at the numbers and that the release angles are constantly going up. Seeing what the patterns are we notice in the numbers, but it's pretty challenging to notice a pattern when we're just looking at a data table. It's a little bit easier if we get to look at graphs. Some people made bar charts, and bar charts can help you look at patterns. And they can be especially helpful when we're comparing things that aren't necessarily numerical, that are more conceptual. So we're actually going to shift to looking at some scatter plots. So here we maybe notice a slight increase pattern, here an increase pattern, interesting. And we have the uncertainty represented here, but it's not currently represented in the graph itself. So then we come over to some scatter plots that have been connected with lines. So you can see the individual points that are plotted. And they're connected with lines, implying that there's a relationship going from one thing to the next thing. And we are trying to figure out what's the relationship between the angle we swing our pendulum from, the release angle, and the period, but we don't necessarily know what that is. And so in general in physics, you don't want to connect your data points with lines. And again, totally fine to have done this on our first lab because what were we expecting? We didn't have any idea. I didn't have any idea. You didn't have any idea. We're just trying things out. And so again, we're noticing that there's some slight increase patterns. We have a little increase, little decrease, big increase. But I have a hard time making any claims about these patterns, being able to say like, oh yeah, it's definitely an increasing thing, because we don't have uncertainty on our data. Uncertainty is really important. And I have a few examples for how it's really important. So here are two scatter plots that aren't connected. And I want to talk a little bit about how we can represent uncertainty and how important it is. And to do that, I'm going to use an example that you might think of as not science, but actually, it's a lot of science. Science is all about making models that describe the world that can help make predictions. And so I'm going to look at some models from political science. So this is a model that's predicting who is going to get the majority of the vote in the 2012 election. So you were like in elementary school then. Probably you don't remember this. And you maybe remember that President Obama won and it was predicted he would win with 50% of the vote. Mitt Romney was predicted to get 47% of the vote. But what I really want to point out is that there's this thing called margin of error, and that's actually uncertainty. And this uncertainty is plus or minus 3.5 percentage points. Notice 50, 47. If I have plus or minus 3.5 percentage points, that actually means that Mitt Romney could be as high as 55.5. And President Obama could be as low as 46.5%. So the uncertainty representation and recognizing that it has an impact is super, super important. In later elections, this is our 2016 election, which you probably do recall, we have some different representations of uncertainty. So here we have a median line of what this poll or this data has suggested the results of the election would be. But then there's this blue area of uncertainty and red area and yellow, but we won't care about that. And so what you notice is that although the polls and the like equations, mathematical models that they used from that data from the polls to predict who would win, indicated that Hillary Clinton would win, and you might recall she did win the majority of she won the popular vote, but not the Electoral College. But what we're seeing here is that there's this like area where the areas of uncertainty overlap. So the mathematical model that was used to make these predictions is saying, well, actually, we think that Hillary Clinton will be higher, but we have some uncertainty in that. And the same thing with Donald Trump. And so our election results actually came out in the Electoral College side to be in this area of uncertainty. And we can use that to look at the current election that's going to be happening in November with former Vice President Joe Biden and current sitting President Donald Trump. And again, we have some predictions, but these error bars are really important to understand the meaning of. So if we look at the key here, we have a median, that's the line. Median means middle result. And then we have these confidence intervals that's telling us how much confidence they have that it will be in that range. And we can still see that there's this area of overlap. There's this area of, well, we're not quite sure if the Biden result will be here or somewhere in here. So they have 95% confidence it'll be somewhere in here, 60% confidence somewhere in here. And so we're not 100% sure, even though they have these mathematical models that are meant to help predict the results. And science works very similarly. We want to represent uncertainty so that I can say, oh yeah, I have there's a high chance of rain tomorrow. We use scientific models to predict the weather. And so I might say, there's probably going to be rain, but I'm not, there's this chance that if the weather pattern does this thing that we can't quite predict, that maybe there won't be. And so that uncertainty informs the way we give predictions and the way we understand our results. So in our pendulum lab, we want to understand our results with uncertainty. Here we just have our scatter plot with dots. And here this person has done a really interesting thing. They have plotted all of their data points. So you can see that for each angle, there are 3 data points, which is kind of cool because that means they're showing the spread of their data, the spread of their results. And that's actually a way to represent uncertainty. Another way we can represent uncertainty is with error bars and error boxes. And both of these are totally valid. We will use both at different times. I don't remember, I think Desmos will make error bars for us, but not error boxes. And the computer program we'll use when we're physically at Harding called Logger Pro actually does both really well. But the whole point of error bars and error boxes is that you want to represent how much uncertainty there is in your result. So when I'm thinking about the period, I know that human reaction time is plus or minus 0.4 seconds. It's plus or minus 0.2 seconds, but since you have to click twice, that adds up to 0.4 seconds. So I have going up 0.4 seconds and down 0.4 seconds, and I maybe scaled it correctly. Um, and additionally, when you were measuring your angle, I'm pretty sure that it wasn't always exactly 5 degrees, exactly 10 degrees, exactly 15 degrees. And so you need to think through, well, what is the measurement uncertainty on that? You might say, oh, well, the protractor has plus or minus 1 degree as a measurement uncertainty for the protractor. But personally, when I was getting my data, it was not as easy as that. And so I actually have it looking like more like maybe 2 degrees. You could even have these error bars be larger depending on your justification for how much uncertainty you have in your measurement of the angle. Error boxes are doing the exact same thing except at the box. Yeah, pretty exciting. And so that's actually something that's kind of important to point out here, that the area of uncertainty isn't just anywhere on these two lines. It's anywhere in the imaginary box that is around it. And if I draw the imaginary box, then it's anywhere in the real box. Anyway, so what these are showing me is that there's actually a pretty large spread in possible data points. And so what I want to do is say, okay, well, I have my uncertainty. How can I answer my question? How does changing the release angle change the period of the pendulum? So to do this, I'm going to look at my data and I'm actually going to put some lines of best fit. And some of you thought like, well, maybe it's increasing. And we had seen that there was this like partially increasing pattern here. On some previous data, there have been some more clear increasing patterns. But once we put in our error bars, something fishy kind of shows up. And that is that with the amount of uncertainty in each of our data points, there doesn't really seem to be very much of a pattern going on at all. Well, wait a second, Ms. Guess, you're wrong. There is a pattern going on. It's just really boring. And that's because it doesn't seem like the period is changing very much. And so I can just draw a flat line, a line that just goes straight across. It's a little funny on the angles on my graphs here, but I'm just drawing a flat line. It has no slope. And that's because that's the simplest pattern that does fit within our error bars. And we'll be looking more next week at mathematical patterns and how to fit them to our data on Desmos, actually. And so what this is telling us is that as the release angle increases, the period of the pendulum stays the same. And some of you, I remember from class, even predicted this. Some of you said that because the further you pull it back, you might think it will take more time to swing back and forth. But you said, it might take more time, but it actually will be going faster. So you kind of thought those two things would even out. And you were actually totally right. Those two things do even out, and the pendulum's period does stay the same. This mathematical pattern is called a flat line, pretty boring, and has the equation y equals, would that be in math class? Take a moment, think about it. I'm going to say y equals b. So you remember y equals mx plus b. Well, on a flat line, there's no m, there's no slope. Slope is equal to 0. So that means x doesn't matter. So then y is just always the same thing, y equals b. So that tells me if I had a release angle of like 45 degrees, I would still predict the same period of the pendulum as I got at 10 degrees and 20 degrees. Okay, so next week we'll be looking at another lab. We'll be collecting data, we'll be trying to process it and then understand it together on that week of MEA. So you want to be all caught up with your IB physics work for this week, and do come to office hours and get help if you need it. Thanks, guys.